Okay, so we're going to be looking at how we decide which of the tests we should use when we're trying to decide if an infinite series is convergent or divergent. So we've seen many tests, and so you might wonder, when should I use which ones? So here are some guidelines for how we can approach this. So first of all, if the nth term does approach 0, then that's certainly a quick and easy test to show that the series diverges. So remember, the nth term test is a divergence test only. So if you can quickly just look at the limit as n goes to infinity and you see that it's non-zero, then you're done. You know it diverges. If that doesn't happen, then maybe the next best thing to look for is the series one of our sort of special types? Is it geometric or a p-series or an alternating series? If so, all three have fairly straightforward tests that can be applied. And then after that, if it's none of those, then you can think about, can you integrate the expression a sub n? If you can, then you could try applying the integral test. If it's an nth power, then the root test might be a good idea. Or if it looks like some sort of ratio, the ratio test may be applied. And then the last thing you might try also is, if your series is not one of these sort of special types, can it be compared to one of the ones using either a direct comparison or a limit comparison? Now, there will be definitely some cases where more than one test is applicable, so what you want to try to do is just figure out which one is the most efficient test to use. And so what I would ask you to do is, as you do the problems in this section, or as we work through them, you might want to always be going back to this list of questions, of guidelines. Okay, so when we look at some examples, in all of these examples I would ask that you first think about, can you actually figure out if the series converges or diverges before you look at what I do. Since at this point we're really not learning anything new, we're just reviewing all of the tests at once. So in this first example, think about what you would try. What I notice here is that if I take the limit as n goes to infinity, I see that I get 1/3. Since this is not 0, we can say that this series diverges by the nth term test. And you'll notice that in this section, as we do all these problems, I will be looking for the work that you're doing, your conclusion, whether it diverges or converges, and then what test you used. Let's try another example. Okay, you should note that this is a geometric series. And so what does that tell you? Since we know r is pi over 6, we know that's less than 1. So because pi is 3.14, so that's about a half. So we know that this converges by the geometric series test. If we were asked to know what this converges to, we also could find that, since remember we have the formula that a is equal to 1, the sum would be equal to a over 1 minus r. In this case, a would be pi over 6 to the first power, so just pi over 6, and r is also pi over 6. Now we weren't asked to do that, but that is just something you should know. Also note that you could have used the root test here, and you'd get the same result. In this next example, this is sort of screaming integral test, since we can see that we can do a substitution. So we evaluate this improper integral by taking the limit as b goes to infinity to make this proper, and we can therefore apply the fundamental theorem of calculus. We do a little substitution, but notice that we need to input our -2 out front here, and so we put the -2 in and the -1/2 out front, so we can do our substitution. So everything in highlighted or underlined in green is just our du, so we just have e to the u du. We also have to change our bounds. When x is 1, u is -1 squared, which is -1. Note this is not negative x quantity squared, so it's not the -1 being squared, it's the negative of 1 being squared. And then up here we're going to have our negative b squared. Since the antiderivative e to the u is just e to the u, we now apply the fundamental theorem of calculus. So when we substitute in our n values, notice that this is the same thing as 1 over e to the b squared. So as b goes to infinity, this whole term goes to 0. So we have this -1/2 times 0 minus 1 over e. So this goes to an actual value, so this series converges. Or really what I should say is the integral converges. And since the integral converges, that tells us that our series converges by the integral test. As we look at this next example, the nth term goes to 0. This is not a p-series or geometric. It doesn't look like it's not alternating. It doesn't look like ratio or root test is going to help us a lot. But a comparison would be very easy, because notice that if I compare this, you can either compare it to 1 over 3n or just 1 over n. Either way, it's a divergent p-series. So we see that adding terms in the denominator here is going to make this whole fraction going to be smaller than the terms over here. So we can't use a direct comparison because being smaller than a divergent series isn't helpful, but we can use a limit comparison. So we take the limit of the ratio of the two series. And we see that we get n over 3n plus 1 here, so this limit is going to go to 1/3. Since this limit exists, this tells us that both series behave similarly, so they must both be divergent. This one is clearly an alternating series, so we could use the alternating series test, which is what I'm going to do. You could also try other tests, but let's just use alternating series test. So here a sub n is 3 over 4n plus 1. So we're looking for two things. Does the limit as n go to infinity of a sub n equal 0? And is the nth plus first term less than or equal to the nth term? So over here, the limit as n goes to infinity of 3 over 4n plus 1 is, of course, 0. And if we look at what happens when we substitute n plus 1 into the denominator versus just the original series, we see that making the denominator bigger will make the entire fraction smaller. So yes, this one is true also. So this converges. But now, since it converges by the alternating series test, we still have to test to see if it converges absolutely or conditionally. So what that means is we have to look at the new series, and let me scroll up. We look at the new series without the -1 to the n parts. We look at this series and ask ourselves, does this converge or diverge? So what do you think? Does this converge or diverge? Well, as in the last example, this looks very similar to the harmonic series, so we can do a comparison to this. And if you in fact do that, you'll see that this series diverges as well. So since the original series converges, but the positive terms diverges, that tells us the original series converges conditionally. And you should check that all my computations that you get the same thing. Okay, in this next example, I see factorials, which usually leads me to try ratio tests. I'm going to go ahead and do that. And I'm going to assume that you guys follow that if I'm dividing, I can flip and multiply here. So make sure you write that out and you understand that step. And I just put my absolute values there. So we see some things cancel. And we're left with the limit as n goes to infinity of n plus 1 over 10, which clearly goes to infinity. So this series diverges by the ratio test. We've got one more example here, and then you'll be trying some in class. And so notice that this is to the nth power, so automatically I'm thinking root test. So let's set up our limit, and we see that the nth root and the nth power cancel, and so we get a rational function whose limit is 1/2. Since this is less than 1, this tells us that our series converges, and it converges by the root test.